Welcome everyone. So today we're going to discuss about D'Alembert's principle. So D'Alembert's principle in classical mechanics is one of the important concepts, and it transforms dynamical problems into static equilibrium problems. Now the definition of D'Alembert's principle. It states that for any system of particles, the sum of the differences between the externally applied forces and the time derivatives of the momenta is zero when projected onto any virtual displacement. So mathematically what it is trying to say, we're gonna see. Okay, now the mathematical foundation of D'Alembert's principle. So Newton's second law is traditionally expressed as F equals to ma, where F is the force and ma is the acceleration. Now D'Alembert's principle rearranges this mathematically, this equation into summation F minus ma is equals to 0, or mathematically for ith particle we can write it as summation I a phi minus mi ai dot delta ri is equals to 0. So here a phi is the total applied forces and mi ai, this term is the time derivative of momentum, and this delta ri is the virtual displacement. So the D'Alembert's principle can mathematically be written in this way. Considering this minus ma or inertial forces, we can actually convert our dynamical problems into static equilibrium problem, and that's the magic of D'Alembert's principle. And the beauty of D'Alembert's principle is that it can simplify our mechanics, eliminate constant forces from our calculations, and also a key concept for our advanced mechanics. This was our discussion on D'Alembert's principle, and on our next class we're gonna discuss about Lagrangian. Thank you everyone.